hosts. So it's from host to host. Okay, host to host logical communication, whereas this one is process to process. So the processes need not to worry about how it is being carried over the network and all. They don't have to worry. It's the network layer will take care of that. Actually, network layer does this over the network. So many intermediate network devices, okay, and finally bring it over here. All right, network. So that that is there. And we also saw that at the transport layer, we will have segments, okay, segments, and segments will have a portion of data from the application process, and it will have its transport layer headers. Okay. Transport layer headers. Okay. And once it is passed towards the network layer to layer 3, network layer will create its own datagram by encapsulating the segment. We have already seen this. I'm just recapping it. And this would be the network layer header. Okay. These are additional data that are added to the datagram or to the segment to facilitate the correct delivery of the data at the destination. Okay, so network layer header. Okay, and these intermediate routers. Okay. They all depend on these network layer headers. Okay, so these network layer headers, they will process. Okay, processed by routers, intermediate routers actually, routers for correct forwarding of data. Okay, correct forwarding and routing of routing. Okay, they will use this. And we also saw that we have two transport layer protocols. Okay, one is transport layer protocols. We saw that one is TCP and UDP. The other one is UDP. We saw this also in our last class. Okay, so that is also another recap of what we have done, looked at. So a number of processes may be running, and also these two layers are providing two different kinds of logical communication between these two layers, between these two hosts. And we also saw an example of how these protocols could work. One could be a very reliable protocol. One could be a very careless protocol, like a best effort protocol, and how data could be lost. All these things we have seen in our last class. Okay. So one more thing. Once again, we have our 5-layer architecture in both sides of the hosts. The data is sent. We have this. We have layer number 3, layer number 2, layer number 1, layer number 5, and 4. And layer number 4, network layer, provides a service model. Okay, a service model. And the layer number 3, the transport layer, also tries to provide a service. Provide a service. Okay. Both are trying to provide a service. And these services that the transport layer try to provide are constrained. Okay, are constrained by the services or by the service model of the network layer. Okay, that is also one important thing that we should keep in mind. Network layer service model. Okay. So that is one thing that is blocking the types of services that the transport layer is trying to provide, because the network layer, it should ensure, okay, ensure that it will give some bandwidth, minimum bandwidth, okay, for the application, minimum bandwidth, guarantees. Otherwise, we cannot develop an application that can use any of these network layer protocols and can send and receive data. Okay, so the if there is no guarantee, minimum bandwidth guarantee, and also minimum delay guarantees, I will try to send data at least within this amount of time. Okay, minimum delay guarantee. If they are not there, layer should provide these guarantees. Okay, then only the transport layer can also provide these guarantees to these applications. Okay, applications. Therefore, applications can send messages between the two machines. Okay, sending host and the receiving host. So the one important thing is, so we can say point to note here. Okay, point to note that these are constrained by the service models, and they are the ones minimum bandwidth and delay guarantees. Okay. Okay. All right. So okay. So in spite of all these, the network layers, minimum guarantees and all, even if it cannot guarantee some, then transport layer is still trying to is still trying to provide some kind of guaranteed services. Okay, so it is also important to note certain services. Sometimes the English may be not correct. I am writing from, but some certain services are provided by the transport layer. Certain services, okay, transport layer, even though the network layer does not we'll see them in a few minutes, does not offer them or guarantee them or provide them. Okay, whatever, as long as the meaning is there. Okay. For example, the transport layer tries to provide a reliable service. Okay, a reliable service through one of its protocols, even though the network layer does not sorry. I did something and I cannot see my the network layer does not ensure a reliable service. Okay, reliable service. Why? In the internet, the internet protocol, it is the protocol of the internet layer. Okay, protocol of the internet layer protocol of the internet layer does a best effort service. Does a best effort service. Okay, best effort service. So in the internet, the IP is a best effort service. In spite of this best effort service, okay, best effort service is a best effort service. That's all. Okay, best effort service. Okay, so best effort service means it does not guarantee a lot. It provides a best effort. Okay, it's not a reliable service. Lose packets or bring out of order packets. Okay, not in the correct order. Okay, garble, etc. Okay, it's not a reliable. Still, the transport layer is trying to provide all these services in one of its protocols. Okay, not every protocol, one of its protocol. Okay, all right. And in the internet, the transport layer provides two protocols. We have covered it a little bit, transport layer protocols. we saw that TCP and UDP. Okay, TCP and UDP, and we also saw that one is one is providing a very reliable service, and the other one is providing a best effort service, and that we have covered very well about the introduction or small introduction to those two. Okay, and we have just seen, I will write it, UDP. TCP is a reliable. The word reliable has many hidden information, and best effort also has just few. In the previous slide I have said what is a best effort service. Okay, and we could also see that, or say that T transport layer, by having these two different protocols running at the layer number 4, just on top of the layer number 3, there is a very well known protocol, and one of them is best effort, and the other one is reliable, and they both depend on this best effort. Okay, and not reliable. Okay, that also you can keep in mind. Okay, and we also saw one thing called multiplexing and demultiplexing. Okay, and these best effort, reliable, not reliable, all these words and their hidden meanings we have covered so many times, and I think I don't need to say it again. Okay, okay, and reliable also I have said so many times. Anyway, once again, to clarify things, so best effort, no guaranteed. Okay, guarantees, and out of order delivery, we saw a few more things. Guarantees of intact delivery. Okay, delivery, all these, and reliable also has so many things. We said guaranteed. Okay, guaranteed minimum delay, guaranteed of. In addition to that, there are a few more things. I will explain them when I flow control, congestion control. No, not now. Congestion control, uh, flow control. Um, this also I will say later, and like sequence numbers for packets. Okay, sequence numbers to identify segments. All these additional things, okay, are part of the reliable data transfer. Okay. One more thing, acknowledgements. When, okay, acknowledgements, all these are there. Okay. In addition to that, the TCP protocol also includes one additional thing called congestion control. Okay, congestion control. Okay, I will spend, I think, at least 1 hour in one of the later classes in discussing what is congestion control. But at a very top level, for the moment, you may recall that congestion control is there when multiple machines are trying to access a common resource, the bandwidth, and that they all want to have fair access to uh, the bandwidth. Congestion control is there. Otherwise, certain application can occupy most of the or consume most of the bandwidth for its data, and the others will have to starve for the bandwidth. So congestion control ensures that all the networks, all the network devices that are all the hosts that are trying to send the data over the network will have a fair share of the bandwidth. Okay, and not somebody predominantly occupying the bandwidth. And therefore, congestion control is applied by TCP, and it's not running on a particular machine. It's running on everywhere over the network by the transport control protocol. And it is run over the internet as a whole, and it prevents someone predominantly of consuming the data. Okay, and it regulates how much an application that is sending data over the network, and therefore it does not predominantly occupy the bandwidth, okay, predominantly consume the data. So congestion control regulates, okay, regulates application processes. Data transfer rate regulates the data transfer rate of applications. Applications or application processes in consuming transfer rates of in consuming bandwidth. Okay, therefore everybody all the application processes will have a better processes will have a fair share of the network, will have a fair share of the bandwidth, network bandwidth. Network bandwidth. All right. So that is also one part of the. And now you can think, one is a best effort protocol and the other one is a reliable protocol. And the for reliable protocol, we list a long list of properties, okay, or characteristics. For best effort, it's few. Okay, most of them are it does not or does not. And for reliable, it does. It does flow control. It does acknowledgements. Okay, so designing reliable transport layer protocols can be complex. Okay, so reliable transport designing them can be very complex. Okay, designing them can be complex. A lot of effort has to be used. Okay, and a lot of resources on the side of the network hosts, and also in the side of the network intermediate network routers will also have to be devoted for these connections. Okay? So those are some of the things. And we also saw one more thing called multiplexing and demultiplexing. Okay, multiplexing and demultiplexing. And simply I showed you a figure and showed how different applications running on computers or hosts. Okay, for example, a host may be like this, and there is this application layer, and for convenience I will draw the transport layer a little bit wider. Okay. Network layer and the data link layer and the physical layer. So when multiple applications run in this host, they all will be, there will be related processes. Okay. A number of processes will be running, and they all will be generating data, and they all have the need to send data to the transport layer requesting service. And for this, when they have data to be sent, the transport layer creates a door for them, which we named as sockets. Okay. This door. Each one will open a door for its, the transport layer opens. Okay. These sockets, and we saw there will, these sockets will be there, and sockets typically created by transport layer. Programmer could also create, when programmers write, when you write your own program, a network application, you may request a transport socket to be created. Okay, I will come back to that in a minute. Created by, typically created by transport layer. Okay. And they are act like door, act like a door for or between application processes and transport layer. Okay, for simplicity, I write it like that. Okay, and so when the data is generated, they need to be sent here. So to send them correctly through the transport layer and to receive them on the other side of the network, the transport layer uses some techniques of gathering these data segments that are coming through the socket and from different applications. Okay, I should also mention that these are different application processes. Okay, it connects, it gathers them. Okay, so one more thing, different application processes generate data. Okay, generate data. Actually, these data are called messages. Okay, and this is messages. These messages are not directly sent to transport layer, by processes. Okay, processes. They are sent through sockets. Okay. Doors. These doors. Okay, they are sent through the doors. And multiple applications generates such multiple data and or messages, and they are sent through the pro sockets. And at the transport layer, it receives data through sockets, receives data or through sockets, and then it creates segments with these information about sockets. Okay, so creates sockets for different applications. You understand that, right? I am not writing everything. So create sockets and stuff data. Sorry, not create socket, create segments. Creates segments and stuff data. Okay, stuff data. We saw this diagram again earlier also, so I'm not drawing it. So when it stuff data, then there is a need. How does it identify this socket? That is why we, in the last class, we saw that sockets have unique ID number. Okay? We saw that also have a unique ID number. Okay? And these ID numbers are 16 bits in length. 16 bits in length. And that gives us 2 to the power 16, something like 65,000, I think 535. Okay. And we also saw that out of this, some are considered as well-known port numbers, 0 to 1023, okay, and 1024 to 65,000 something can be used by applications. Okay, and we also saw that one of these well-known port numbers is port number 80. Okay, everybody knows that for web. Okay, well-known port numbers. We saw this, and I'm just repeating. Okay, and these numbers, they are typically known as port numbers or socket numbers. Okay, port numbers. We saw this also. So each of these segments, when it creates segments and stuff data, it includes these port numbers or socket numbers that is also get added to this. Okay. So whenever it receives data from multiple applications running on machines, it receives them, couple them with segment numbers, or sorry, couple the segments with socket numbers or port numbers, and send them through the send them as segments and passes them down the network layer. This process is called the multiplexing. Okay, receiving from multiple places or sharing something, whatever. And then when it arrives at the receiving host, also, layer number 4 is there, layer number 5 is there, and 5 will be having multiple processes running. And in the receiving side also, there will be a number of sockets, and when data arrive to from the network layer using the socket number, it delivers these packets to the correct sockets, okay, using by identifying, and this process is called the demultiplexing. Okay, so the multiplexing and demultiplexing process uses socket numbers or port numbers, okay, and to identify and correctly deliver the data towards the correct application processes. Okay, so something we can say, so sockets have unique IDs. And segment headers will include these socket IDs, okay, which we call as port numbers. Okay, I will show you an example. Okay, and there will be other in the segment, there will be other header information. Okay, there will be other header information too, because now we are sending data. Okay, we are sending data, and we are sending it from one machine to another over the network. The segment is being sent, and we need to identify these hosts. Okay, identify these hosts. So each host will at least have one IP address. Okay, each host will have at least one IP address. Okay, address. So that could also be included into the segment header. Though IP addresses are used by the network layer to send and receive data, the IP address information could also be used by the segments. Okay, could also get included into the sockets. We will see why these are, why is it so. Okay, and in addition to this, when data is sent from source, it is sent and will arrive at the destination. So we just saw in our previous example, previous diagrams, okay, there will be sockets here, couple of sockets. There may be a couple of sockets in this machine also. Okay, sockets. So they are sockets, and since this is source socket number or source port number. Okay, they are called source port number. At the same time, at the destination also there will be ports, so that is called destination port number. Okay, so they will be included into the datagrams, and these in addition to the other fields. Okay, these socket IDs. So when I said this is what I was referring to. Okay, they will be included into the segments. Okay. And we saw these well-known port numbers 1024 and everything. And so a transport layer also does this multiplexing and demultiplexing. These are also services provided by the um, transport layer. Okay. And, earlier I said when there is an application process and the net transport layer and there is a socket. Okay. The socket is created and the port number is assigned by the transport layer. Okay. For example, 80. Okay. 80 is a port number assigned for web. But it could also assign a number between 1024 to 65,535, especially for UDP applications, UDP processes. Okay, that could also take place. Okay. In addition to that, we could also see a programmer, somebody interested, could also request a port number using network programming commands, okay, to be used by his or to be used in his program, in his application, in his application. Okay. That is also possible. Okay, so let's see a small example. Let's see. Here is host A. And here is host B. Is this application layer. There is this transport layer. And similarly, here also we have 3 layers. And we will say this port number is 19,157, some number. And this one is something like 46,428, some number between 1024 and 65,535. Okay. So what happens here is the transport layer creates a segment. Okay. Segment. And this will include as source port number and destination port number for with the known values. Okay. So source port number is 19,157. Destination port number is 46,426. And in addition to this, the data and the other headers will also be there. Okay. Other header information will also be there. Okay. So then this one is passed to the network layer. Okay. And will ultimately arrive via the network layer on the other side of the host P. Okay. And whenever it arrives, this number is checked and it is sent through the correct port. Okay. And in this case, we have just assumed exactly one process. Okay. But there may be other processes, okay, with different numbers. Okay. Okay. So maybe this one is 8,000. Oops, sorry. 8,593. Okay. This one 6,347. But by looking at the port number, even though there are multiple chances of delivering the segment at different sockets or ports, the packet is delivered or segment is delivered correctly at the correct segment. Sorry, correct socket. Okay. So in addition to that, we also just saw in our previous discussion hosts. This is host B. Host B. So IP address of B is also there. Okay. Similarly, this is host A. So IP address of B is A is also there. Okay. IP address of A is also there. So when data is arriving or when data arrives, okay, when data arrives, the socket, okay, or the segment will be identified by IP address of P and the socket number or port number. We'll say port number and port number. Okay. These two information would be used to bring the data correctly to the destination. Okay. So if you look into a smaller scale diagram, host A, IP address of A. Okay. Host B, IP address of B, and host C, IP address of C. Okay. Now we'll assume that we are receiving one segment from host A and one segment from host B. So when they arrive, the segment will be having a segment will be there. Okay. And here also a segment will be there. Segment. Here the arriving two segments will have, okay, they have their own source IP, and source IP and source port number. Okay, source IP and source port number. Give me 1 minute. Source IP and source port number. Okay, but they have both have same destination IP and destination port number. Okay, and I forgot to mention here, they have their own port number and source are different. These are different. Okay, both are different, right? So it will be different. So when they both have the same destination IP address and destination port number, their data will be delivered to the same socket. Okay, remember, keep in mind that they will be delivered to the same socket. This happens with UDP packets. Very often it is the case because UDP uses destination host address and the destination port number to identify the receiving socket. Okay, will be delivered to the receiving socket. Okay, then the question arises, then how does it send the reply? Of course, they both have source IP address and the source port numbers, so they will be used. They will be used to send back the reply to individual machines. Okay? So that is how the UDP protocol works, and there is no unique connection. The multiple machines may be sending data to a single socket. Okay? That is the point to note here. Okay. Multiple processes will be sending data to the same code or same process in the destination. Okay, that is one property of this UDP protocol. Okay, and if anybody asks what are some of the qualities of a UDP protocol, it's a best effort protocol, and it uses it uses destination port number and the destination IP address to identify the destination ports, or to identify the process at the destination. Okay, process at the destination. But a UDP segment will contain the source port number, source IP address, everything is there. Okay, but they are not used to identify the process in the destination, or to correctly identify the destination. Okay. Okay. So just keep in mind that this is something very odd with the UDP protocol. But UDP protocol is the one very well used for DNS. Okay. And so it is a best effort. I can write something again about DNS or UDP protocols, like small notes. UDP is a best effort protocol. So not a very some best effort protocol, and uses destination IP and destination port number to identify the destination process. To identify the destination process. And because of this, multiple sockets arriving from multiple hosts could be delivered to the same destination process. That is also one thing, okay, that we have heard about that. Okay, and so you may just remember this. Okay, at in a segment, source port number plus source IP address is included. Similarly, destination port number, destination IP address. The UDP segment. Okay, they are used. And in addition to this, few more additional information could also be used. Additional few more header information are also added. So UDP segment header. This is the header. So additional header information are used. So when the data is sent from host A to host B, it has IP of B. Oops. IP of B. This has IP of A. It's not IR, it's IP. Okay. IP of B. This is IP of A. Okay. Similarly, a port number in A, port number B. So when the segment is created, it is represented like this. Port number A and IPA source. Okay. And port number B as the destination and IP of B. Okay. This is the one. And this sent. And when the reply arrives for this sent segment, sorry, bad English. When the reply arrives, okay, now we are going to have again source port number. Oops. Arrives. Okay. Now this is the source port number B, IP address of B. Okay. Port number A, IP address of A. Okay. They switch their positions. Okay. That happens with the other one also, port numbers also. Okay. They switch their positions. So source and destination, they change and they are sent in the different order. Okay. And with all these, so not a lot of issues and all. So we saw that we just design, we can just create segments just with 4 information, and only 2 information is used by the destination machines to correctly identify the receiving segment or the receiving port number. Why is this kind of protocols used in applications or application designs? So UDP protocol, what is the motivation behind it? Okay, very simple to design. You just need only 2 information that can be used to identify the destination socket number. In addition to that, our segment header is also lightweight. Okay, so we can say lightweight segment header. lightweight segment header. Okay, and it's just best effort. Okay, best effort, no additional difficulties. So it's called no frills service. Okay, no frills service. That means a frill is a piece of cloth that is attached to a shirt, trouser, frocks, skirts, etc. with a name tag. For example, in Jen's shirt, in the back of the collar, we can see something like signature. This piece of cloth is the frill, attached cloth. What does it say when you say it is signature? Some certain guarantees and certain guarantee that this is a full sleeve shirt. Both hands will be of the same length and they will not shrink when you wash them in a washer. Okay, and it has a style, it has a cut, it has a stitching style, quality things used, buttons and everything. It is guaranteed. So that is guaranteed with this frill attached to the shirt. Similarly to a trouser, to a coat, to a frock, to a skirt. Okay, everything. But UDP is a no frill, no guarantee, nothing. It just you send and you expect the transport layer to deliver the segment at the destination. Okay, so it's not taking much effort in sending this segment towards the destination machine. Okay, but it does provide the multiplexing and demultiplexing services, of course, but it does not take much effort. It takes best effort. Okay, and UDP is all providing that kind of service. And in addition to that, when we have two machines, host A and host B, suppose UDP in action or UDP wants to be in operation, wants to be in operation between these two, it just prepares the segment. Okay, it just prepares the segment, and sends the segment, and it expects that the segment arrives at the other end and segment will be the destination will send a reply. Okay, so I'll say this is the destination machine and this is the host machine, source machine. Source machine, and so at the source it prepares this segment, okay, and sends the segment. And something to note, we'll assume that it arrives. Okay, sometimes it may not arrive because of the networking, but we network's best effort service, but now we'll assume it arrives. Okay, then it is successful and we hope that a reply will be sent. Okay, oh no, a reply may be sent. Okay, a reply may be sent. And whenever it prepares and sends, it does not talk to one important thing. And when it prepares and sends the segment, it does not talk to the destination in advance to check whether it can send the data, whether it can send the data or segment, and if the destination is willing to receive it. Okay? If the destination is willing to receive the segment. Okay? It does not check, it does not talk to the destination. Okay? And it just sends and expects. Okay? Of course, this kind of thing makes the design of the protocol and the operation of the protocol much easier. You prepare the segment with all these data and segment chunks of data with all the source port number, destination port number, source IP address, destination IP address, and you just send and forget it. Okay? You don't talk to the destination in advance. Some protocols are designed in a different manner and they talk in advance. Okay? And when they do talk and then they start sending and receiving data, that process of talking in advance or talking with the other side of the communication and making sure the other party is ready to receive the data is called handshaking. And here, since this one does not do the talking, this is called a no handshake. Okay, like when we meet unknown people, we talk before we talk our business. Before we talk anything, we just do handshake and we exchange some pleasantries. How do you do? How are you? And then we start to exchange our business talk. So that is in protocol design, especially these transport protocols also, that activity is there. And that is called a handshaking. Whichever protocol utilizes this handshaking process is called a protocol or a handshaking protocol. But in this case, with UDP, there is no handshake. It just sends data and assumes it will arrive at the destination. Okay, UDP just sends data, just sends segment and hopes it arrives and hopes it arrives. Okay, it arrives at the destination. Okay, and this property or this thing, this makes the protocol design and operation much simpler. Okay, much simpler. So applications can also be designed in a much simpler manner. They don't need to bother too much whether the other party is ready to design, receive, whether they can acknowledge a lot of things. That is not here. Okay, so UDP allows us to design simpler protocols, and simpler protocol design implies that our application could also run without much trouble, or can be designed without much trouble. Okay, so this property, UDP's simple design or simple operation, is well utilized for DNS. Okay, DNS. You remember DNS, domain name system? Okay. Um, um, so in a DNS hosts to some server. Okay, server. I don't mention which server because there are root servers, there are authoritative server. I'll say just okay, DNS server. Okay, authoritative server, top level domain servers. So UDP, on top of UDP, DNS query is sent, okay, with best effort in mind. Okay. This best effort implies may arrive or may not arrive. Okay, may not arrive. So what happens when a DNS query, by using this, when a DNS query did not arrive? So there is a browser which sent this DNS query and the reply did not arrive. So what do we do then? Send it again. After waiting, for a certain period of time, send again. Okay, because these queries responses are not very time sensitive or very serious in my information of concern, so you can just send, excuse me, you can send and wait for the reply. Okay, it can resend the query again. Okay, so in then naturally people can ask, if multiple fails, multiple times you fail, you don't get a reply, then what do we do? We are talking about DNS servers. Okay, you can connect with the same color line that are using root servers. Okay, top level domain servers. Okay, or authoritative servers. All these. What do we know about them? There are multiple such servers. So even if it fails, what do? We can send a request to another one. Another one. Okay. So UDP and the DNS requests are designed in such a manner even after multiple tries. If it fails, you may send it to another one, because whenever the reply comes from your previous requests, when root servers tell about top level domain servers, they send you a list of top level domain servers. When top level domain servers send you a reply, they send you a number of or a list of authoritative servers. So you don't just have just one server, you have multiple servers. So you can, after multiple failures, you can send your request to another one from your list. Okay, so DNS operates like that. And why do then one more thing? We have been looking at UDP and its simpler operation. Why do application programmers prefer UDP? Why do they prefer UDP over TCP? We haven't seen TCP a lot, but why does anybody? It's not a very reliable protocol. It's just a uh, um, mm, any guarantees. A lot of issues are there. Then why does anybody prefer to have UDP protocols? It means it provides a finer application level control. Okay, and you just design or you decide what data is going to be sent and when. Okay, so and there is no handshaking and all, so it's very immediate. Okay, so it provides a finer application level control. And when, okay, you remember when we said the UDP protocol, I said no handshaking. Okay? No handshaking. So this implies no additional time or resource additional time or resource. Oh, data transmission. Okay? No handshaking. No, all these. And no handshaking, blah, blah, blah. Uh, it also provides a best effort service. best effort service. Okay. This implies data losses are possible. It automatically deletes. Data losses are possible. So, is that a serious thing? Data losses are possible? Yes. When you lose data, that seriously affect the quality of the data. Okay. But for some time sensitive information, for some real-time applications, when you watch some movie or some real-time cricket match, okay, some real-time applications, streaming applications, not everything, okay, some. Because when you pay credit by credit card and watch a movie online on Netflix site, you will not tolerate data losses. Okay. For that, we will have different protocols. But here, when we have something like a free services, free applications that enable us to watch some real-time video streaming, blah, 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 some real-time applications can tolerate few data losses here and there. Okay, few data losses. Okay, so easy design, easy implementation. Okay, simpler implementation. No very hard or very time-consuming handshaking, everything. Okay, that is also one reason for having UDP protocols. No handshaking is one good thing, and we have seen. And so we saw that the DNS is used by HTTP for this IP address to, sorry, the mnemonical names to canonical name, or from canonical name to mnemonical name mapping and all. Okay. And since there is no handshaking, as I said earlier, no handshaking, that also implies no connection states. Okay, connection state. We don't just connect, we send data and assume the other party receives the data and we will get a reply. Okay. So no connection state, and that implies no need to maintain connection information. Connection information. Connection information, we normally keep them in variables. So no additional variables to maintain connection information. And because of this, we could also have a smaller segment header. Okay, because we don't keep too much information. So smaller segment header. Okay, so that is also there. Okay, so these are some of the reasons why an application programmer may choose or might choose UDP protocol, which is the best effort and does not provide any guarantees or does not provide a reliable service, and can lose packets and all these drawbacks, and it's a no frills protocol, then why do people prefer it? Okay, so that are some uh, reasons. Okay, and and I think that with that we can conclude the design or the discussion for designing UDP protocol. There is one more small thing to look at: the UDP protocol segment structure. UDP's segment has not much information. It has very little information. So we can cover it up, and then UDP segment structure. Segment. We earlier saw that segment will have header information. Yes. For convenience, I will use a 32-bit length box to indicate the segment structure, even for UDP, TCP. And when we go to the network layer and look at the IP protocol, I will use the same structure. Okay. Typically, it will not be like this. It will be like a very lengthy thing like this, a series of bits. But drawing like this and partitioning and understanding is difficult. So I will draw it in the other way. Okay. Okay. So 32 bits and 16 bits are used. So exactly in the middle, 16 bits are used for source port number, and 16 more bits are used for destination port number. These are the two important things. Okay, and of course the source IP address and destination IP addresses are there. That will be included by the uh, network layer. And in addition to this, a 16-bit length of 16 bits long length information about the segment is included. And then 16-bit checksum is also included. Okay, checksum. I did not tell about this checksum earlier. And then the data will follow based on the size of the segment. Okay, so very little smaller header information. Smaller header information, and this checksum will be used for error checking. Error checking purposes. Okay, and when data arrives, data may arrive with errors. Okay, and checksum we can use parity bit based checksum. It's very simple one, parity bit based checksum techniques. Okay, or some other advanced checksums. Okay, and you have already heard about these parity checks, and also I think we don't need to look in much into these checksums. Typically, these checksums will help us to detect errors. Okay, and then you will have to, your application process will have to decide what to do. when you find an check segment that carries errors, okay, to detect errors. So when the errors are there, you decide whether you want to accept it or reject it. Okay, or reject it. Okay, when you want to accept it, you will have to correct the errors. Okay, correct. Otherwise, the data is still having errors. There is no point in data with errors. Okay, so you will have to your application logic will have to decide on what to do with this data. Okay, so if you want to do corrections, then your algorithm of and these checksum algorithms will have to be a little more knowledgeable. They should have some cognitive things with them. Therefore, they can determine where the errors took place and how do they correct those errors. Okay, so those algorithms can be really expensive because they expensive mean not monetary wise, but they require a lot of knowledge, lot of CPU cycles, and you will have to spend some time in correcting the errors. At the same time, the application programmer should keep in mind that the data is arriving at a very high speed. So if the data is going to be get corrected and then to be sent to the upper layer, then it's going to take too much time. So the application designer may reject the data, okay, and just forget it because there is no correspondence between the sender and receiver. They may reject the data and then expect the sender to send the data again. Okay, and this error checking is maintained as a simple with simple algorithms. Okay, so these checking purposes and are used, and no, that is not a correct English, and employ simple algorithms. Simple algorithms. Okay, algorithms. Okay, and in addition to that, the internet protocol layer at layer 3, it's also going to have some sort of smaller error checking, but that is also not uh, uh, very well designed error checking. But here, UDP is trying, in addition to the network layer protocol, UDP is also trying to give and implement some small set of uh, 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 error checking algorithms. Okay, all right. So typically, they are simple and this and UDP with errors. UDP does not employ error correction mechanisms. Okay, does not employ error corrections. Error correction. Okay, so UDP. So then, what does it mean? Does not employ employ error correction? Just discard. Okay, if the other guy wants, they can send again. Okay, it all depends on how the protocol is designed and developed. The UDP designers, they just say we want to have it to be very simple protocol. Okay? And therefore, when we detect errors, we do not accept. And we will just discard the data segment. That's all. Okay. All right. And I think that's all mostly about UDP protocol. And next, we will look into TCP protocol. I will also add a few Python programs for these connection establishments and this how they exchange data and to look at. If you have, they are in point of view of exams, they are not needed. But if you have some free time, you can try and run these programs in a Windows laptop or a Linux machine using Python, and can see that how these programs are running and they are exchanging messages. Nice to see. Okay. All right. So let's move on. Let's uh, start a little bit of discussion on UDP protocol. So CP protocol, TCP protocol. It's, as I said earlier, it's a reliable protocol. Okay? This reliable has many meanings. Okay? Implies many things. In order delivery of data. Okay? In order delivery of data. And guaranteed delivery. Delivery. And it also will use a number of variables to maintain connection information. Okay, connection information or connection state. Okay, connection information or connection state. All these are there, and because of all these, it uses a handshaking beforehand. It employs handshaking. We could also say it's a handshaking protocol. So connection before sending data, you establish the connection. Okay. Before sending data, establish connection. Establish connection. Okay. And while the connection is established, you send and receive data. Send, receive data. Okay. Once send and receive data is over, you disconnect. Okay. Disconnect the connection. Okay. So all these things are there. So because of this, you establish a connection, you send and receive, you disconnect. And this is all require a lot of effort. Okay. They all require a lot of effort, require a lot of resources. Also effort, lot of resources. So the devices will have to reserve resources, okay, and have to be in contact. I'll draw a small diagram to explain that. When we have two hosts, host A and host B, to send and receive data when they want to send and receive data. So when they want to use TCP protocol between themselves, okay, before doing anything, they will have to establish a connection. Establish a connection. Okay. While the connection is in progress or is inactive, you send and receive data. Send and receive data. At certain point, you decide that it is enough and the data transfer is over, then you disconnect. Okay. And when you say send and receive data, this is a long process. A long process. You maintain state, connection state. Okay, you maintain state, and you ensure receipt of data. Okay, you ensure receipt of the data. Then you also worry what to do when data losses. What to do with data losses. Okay. So many questions, so many things. These all imply in so many state or connection variables. Okay. Connection variable. Connection variables. So whenever the connection is established, they both use their memory space allocated for this connection. Okay, they both from their hard drive, their memory space, they allocate variables, resources for this connection. Okay, memory variables. Storage space, everything for this particular connection. So it's a lot. And so when the connection is established, they all are reserved for this connection. Okay. When you establish this connection, memory variables, storage space are all reserved and kept for this connection. Okay. On both sides, they also do this. And when the connection is, when the data transfer is taking place, the data is exchanged here and there, and variables are updated, memory storage is released, memory storage is acquired, and at the end of the this connection, all these are released. Okay? Released, or we can say evoked by the operating system. Okay, they are no longer needed, so they will not be used. Okay, so this is what a reliable connection establishment or reliable data transfer needs us, requires us. Okay, you establish the connection first with the other side. So establishing a connection is one thing. Then you send and receive data back and forth. And at certain point, either of the party decides that no need for data transfer. So they agree to disconnect the connection. So they evoke or release the data that has been allocated for the for this particular connection. Okay? And connection establishment is also one important thing. Okay, you establish thing. So when you establish, you agree for something. Okay, you agree for some connection establishment, and you guarantee that certain things, certain memory variables, certain storage space will be allocated for this. And whenever you ask me something, I will send you the reply. All these guarantees are there. Okay, so the establishment itself is a protocol. Okay, how to establish. When we meet a person, when we meet an unknown person or a strange person for the very first time, and we are supposed to start a business deal with him, and we are about to talk to him in a cordial manner for a longer period of time, but we are supposed to initiate the connection, initiate the discussion with that person. Whenever we are in front of that person, we extend our hand towards him. Okay, why? To show him that we are ready to handshake with him. Handshaking means we are about to start a conversation. We are about to start a pleasant conversation, a pleasant ice-breaking event. Therefore, to start the conversation, start the business. So we do all these by following a protocol. We smile, we exchange certain words. Hello, how do you do? How are you? Did you have a safe flight or a safe journey or a nice journey? Or when did you arrive? And we shake hands a couple of times, and then after a while only we really start discussing about the business. So how do we establish a connection? There is also a protocol how to do that connection establishment. Okay, once that protocol is done and it is nicely established, then we come to data exchange part. Okay, so this is what TCP protocol is doing in comparison to the UDP protocol. TCP protocol is doing a lot. It establishes the connection, then sends and receives data. And because of this establishment of connection, it set aside memory variables, storage space, and everything, and then involves in data transfer. At the end of the data transfer, also that protocols tell how do you disconnect, how do you evoke all these information, all these resources that are kept aside for the data. Okay, once that is done, the connection is over. So by following a protocol, all these are done. TCP exactly does or follows this kind of pattern. Okay, so we will continue in the discussion on TCP in our next class. Okay.
Recording stopped.
So I asked for a class on Sunday. Since we have taken an extra class today, I suppose that is enough. Anybody can come on Sunday also for class?